Welcome to Linear Algebra. This is the new course I'm going to start on the YouTube channel today. I am closing in on the multivariable calculus series. I just have to finish with the vector calculus stuff, and then I will be finished with that. But we present a new topic. This topic is usually taken with Calculus 3 or after Calculus 3. And linear algebra is arguably more important than Calculus 3 because it is the basis of many of the things we use today in physics, engineering, and computer science. So, those domains you need linear algebra for. This is going to be the course Introduction to Linear Algebra, and I'm going to be using a lot of the resources from Gilbert Strang's linear algebra course. So some things might actually, like the ordering is pretty similar to Gilbert Strang's linear algebra course. Some things might be similar to Gilbert Strang's linear algebra course. And if I ever assign problems, it will be from Gilbert Strang's Introduction to Linear Algebra book. I think it's in the fifth edition now, but not likely. It's most likely just going to be like the regular um, me lecture and give you examples, and that's going to be it. So this is the course in linear algebra, and you'll be seeing stuff like this, the intersection of two planes. You'll be seeing stuff like this, Graham-Schmidt's. You'll be seeing stuff like this, and you'll be seeing stuff like this. Um, it's the geometry of linear equations. So linear algebra, for those who are oblivious, they might think that it's something like this. It's in middle school. This is linear algebra. This is not it's not non-linear algebra. You don't have to deal any squares, functions, e to the x, anything like that. This is linear algebra. However, this is a lot more of a simple version of linear algebra. For example, solve 3x plus 7 equals 10. Now, if you subtract 7 from both sides, then you'll get 3x is 3, and then x is 1, right? Boom, you just finished your first question in linear algebra, in the official linear algebra course. Of course, you've already done these probably a lot. Solve for y. 4y equals 20 minus 5x. Y equals 20 minus 5x over 4. Boom. You solve your second question in linear algebra. Solve this system of equations. We're going to be dealing a lot with systems of equations in this course because that is the basis of what we're going to represent our equations with, systems. Especially, this is actually called the row picture, which I'm going to explain what that is in the first lesson of linear, or the second lesson of linear algebra. But for now, we're just going to do this. Let's double the second second equation. Why can we double the second equation? Because if you multiply each side by 2, you'll still get the same results for x and y. So let's say this is, well, 4x plus 2y equals 10. And I'm just going to move this equation again here. Now we can add the two equations. So if we add the two equations, like literally just add, why does this work? Well, if 4x plus 2y is 10, and x minus 2y is negative 3, then 4x plus 2y plus x minus 2y is 10 minus 3. So if it's 10 minus 3, that's 7, and plus 2y minus 2y is 0, so it's 5x. 5x equals 7, so x is 7 over 5. Now we can put it back in. I'm going to put it back into to here, actually. So 2 times 7 over 5 plus y is 5. So 14 over 5 plus y is 5. So y is 11 over 5. And there you go. That's your system. 7 over 5. Or that's your solved system. 7 over 5 and 11 over 5. We're going to expand on that a lot. We're going to see under what conditions are these system of equations have infinite solutions, under what conditions do they have no solutions, under what conditions do they have one solution, and etc., etc. right? So this is a system of equations right here. In this course, we will take the linear algebra you learned in middle school and blow it up. It's like multivariable calculus. We're gonna have a bunch of variables. We're gonna have a bunch of conditions. We're gonna learn what it means to perform algebra in different dimensions and with different spaces, with different bases. Basis is a vocabulary term that you're going to hear a lot from me, because it is one of the important ideas, or there's one very important idea in this in this course. It's a giant idea, and basis is in that idea. So very important. And this course is usually, students think it's easier than multivariable calculus. Um, but I'm gonna try to make it maybe equal in difficulty to multivariable calculus by adding proof-based questions like this. Now, if you can solve this, you probably don't need to take linear algebra, because I haven't really solved it yet. I haven't tried solving it yet, but I will probably soon. But anyways, well, I'm gonna add proofs in this course because this course is really the basis, the first proof course that you will see if you are in college. It's not proof writing. It's not a course that it's there just for you to learn how to prove stuff, but it is a course with lots of axioms and theorems that you will have to you'll have to understand in order to utilize those to prove these equations. Not equations, like axioms, identities, I guess you could say. Right? So this is the list of topics that you will learn. So I'm just gonna remove this. You will learn elimination, which you've already learned in middle school. Vector spaces, orthogonalization, determinants, eigenvalues, diagonalization, um, applications like graphs, differential equations, single value decomposition, Markov matrices, Fourier transform, all of that, and matrix transformations. So how do you transform a point from a point, something from a point to another point? You'll learn all that. What are the prerequisites? Now, this is usually offered as college course, but really the prerequisite is only middle school math. So yes, the prerequisite is middle school linear algebra, and you should have the mathematical maturity to know calculus one, or no, you don't need to know calculus one. I'm sorry. For differential equations, you need to know calculus one and two, because we're gonna be doing differential equations. Like 2 episodes of it in this course. We're gonna solve systems of differential equations, and that's gonna use linear algebra, but it's not gonna be a major component of the course. But the prerequisites for this course is middle school linear algebra, and a desire to succeed in a theoretical course. This is a theoretical course. You should be mathematically mature to learn how to do proofs, and you should be coming into terms with dealing with stuff that you might not be able to see with your eyes firsthand. So that is the prerequisites for this course. Who will benefit from this course? All STEM majors will benefit from this course, especially engineering, physics, and math. If you do math, you have to take this course to graduate. So yes, math will benefit from this course. And I think economics majors can also benefit from this course. Um, I know they can benefit from calculus, but I've seen somewhere online that they can also benefit from this course. So, economics, engineering, physics, math, chemistry, biology, all STEM majors can benefit from this. Computer science. I forgot to add computer science in there, but computer science in STEM anyways. So that will be it for today's episode. I don't have any more slides. I hope you guys look forward to learning about linear algebra, as it will be an easy course for those of you who just want to use these videos for a review for your test. And if you want to learn the entire course, proofs and all, then it will be hopefully a challenging experience and a coming of age experience for you guys. Until next time, I will see you later.